We are jumping straight into a massive development in robotic foundation models today, breaking down the paper InternVLA-A1, Unifying Understanding, Generation, and Action for Robotic Manipulation.
Yeah, this one comes out of the Shanghai Artificial Intelligence Laboratory and Intern Robotics, and it really tackles a core conflict that's bottlenecked generalist robots for a while.
And that's the trade-off, right, between understanding language and understanding physics.
Exactly. The trade-off between semantic reasoning and predicting physical dynamics. InternVLA-A1's whole solution is this unified mixture of transformers architecture, or MOT, that's built from the ground up for real-time foresight.
But that architecture is the key. It seamlessly integrates three specialized experts: understanding, visual foresight, and then action execution, all in one pipeline.
And the whole point is creating robustness for dynamic environments. Where things are moving and predicting physics is absolutely critical.
And to feed this whole system, they're using a hybrid strategy they call the data pyramid.
Right, it blends this huge scale of synthetic data, their intern data A1 set, with the physical fidelity of, I think it's over 533 million frames of real-world demos.
So it's a dual approach, really, to try and finally bridge that notorious sim-to-real gap.
And the results are not just incremental, they're pretty transformative. InternVLA-A1 just blows past leading models like Zero and GR00T N1.5.
They're reporting, what, a 14.5% average success rate improvement in just general everyday tasks?
But that's not even the big story. The real proof of concept is in the high dynamic settings. Think conveyor belt manipulation.
Where timing and foresight are everything.
Everything. In those tasks, InternVLA-A1 saw gains from 40% all the way up to a, frankly, staggering 73.3 percentage point improvement over the state-of-the-art. That predictive capability has just fundamentally changed the game.
Okay, let's unpack that core challenge first, because a number like 73.3%, that's a clear signal that something structural was missing before. The goal is the intelligent generalist robot, built on this vision language action paradigm. So why have these MLLM-based models struggled so much with dynamic scenes?
It really comes down to the MLLM's foundational representation. I mean, models like Zero, they're brilliant at semantics because they map all this visual data into high-level text tokens.
Right, so they can interpret abstract commands like make me a sandwich.
Exactly. Or zip the bag with the red label. They get the high-level intent. They can decompose the task.
But those text tokens aren't built for physics.
Not at all. They're inherently weak at capturing dense, continuous physical stuff. They're just not optimized to model things like momentum or inertia or the really subtle dynamics of physical contact.
So if the object is just sitting there, they're fine.
They're great. They give you a reactive perception to action mapping. But the second the environment becomes dynamic, say a package starts rolling on a conveyor belt, that reactive approach just fails spectacularly.
So MLLMs give us the what and the why, but their token space isn't rich enough to predict the fine-grained how of the physics, in the next couple of seconds.
That's the bottleneck. And then you have the flip side, which is the pure world model approach. These are based on video prediction, and they try to solve the dynamics problem by predicting future video frames.
Well, they have foresight.
They do, but they often lack the strong semantic grounding of the MLLMs. They can get really brittle, overly sensitive to tiny prediction errors, or they just fail to grasp the high-level context. They know how the pixels might move, but not why they're moving in the context of the task.
So it sounds like this unavoidable structural trade-off.
Yeah.
You either get semantics or you get dynamics prediction. And this is a problem that just scaling up data couldn't fix on its own, could it? We've seen these incredible data sets like RT1 and OpenX embodiment.
And the paper argues pretty strongly that we've just hit a wall there. They call it the data scaling trap.
The data scaling trap.
Yeah. I mean, large real robot data sets give you essential physical fidelity, but covering every single long-tail scene variation, every weird lighting condition, every slightly different object, every complex contact interaction is just logarithmically costly.
It's a diminishing returns problem. You can't just film the entire universe of physics.
You can't. And so this synergistic hybrid strategy becomes the only real path forward. You need the sheer low-cost diversity of simulation, which is what InternData-A1 provides, and you couple that with the authentic, non-simulatable physics from real-world datasets like Agibot World.
That synergy is how you close the sim-to-real gap.
It's the most efficient way. especially for those really complex contact-rich tasks that are hard even for a human to intuit, let alone a simulator.
Okay, so let's look at the technical solution here.
Right.
The InternVLA-A1 architecture itself, it's a mixture of transformers. How does this pipeline, this understanding to generation to action flow, actually work in a single model?
It's quite clever, actually. It's a single decoder-only transformer, but it uses these distinct experts. The flow kicks off with the understanding expert.
Okay.
This is built on a solid MLLM foundation, like InternVL3. It takes in the multi-view observations, the language command, and it encodes all of that into a set of prefix tokens. You can think of them as the high-level semantic context. It tells the system what the user wants.
Standard stuff.
Yeah.
High-level context.
Yeah.
But then the generation expert is where it gets different, because its job is predicting physics, not just semantics.
Yeah.
Why did they need a whole different visual encoding strategy here?
Because the goal is completely different. The understanding expert abstracts away the details to get to the concept. It needs to know that's a sandwich, not the exact RGB value of a pixel.
Right.
But the generation expert has to predict the future state of the world. It needs to preserve that fine-grained spatial structure, the pixel fidelity, to accurately model how an object is going to move. So they use a decoupled encoding.
And that's with the VAE tokenizer.
Exactly. The Cosmos CI8x8 continuous VAE tokenizer. It compresses the image into continuous latent features which preserve that physical detail.
But we know sequence length is the absolute Achilles heel for transformers, especially if you want real-time control. A big latent map means slow inference. So how did they get the speed they needed?
This is a really brilliant engineering trick. A standard 256 by 256 image gets encoded into a 32 by 32 latent feature map. Now, if they fed all 1,024 of those tokens into the transformer, your inference speed would just tank.
It'd be unusable.
Totally. So their tactic was to apply a final convolutional layer that aggressively compresses that 32 by 32 map spatially down to just 4 by 4.
16 tokens.
Yeah.
To represent the entire visual state for the generation module. That's a massive reduction. Weren't they worried about sacrificing too much granularity?
Oh, absolutely. And it's a clear trade-off. They sacrificed prediction fidelity, so the reconstructed image it generates might look a bit blurry, but they did it in exchange for speed, raw speed.
And that choice was all about real-time control.
It had to be. Both their 2B and 3B models run at about 13 hertz on an RTX 4090. That frequency, 13 frames a second, is what you need for fluid, continuous robotic motion. If it was running at, say, 5 hertz, the robot would just look jerky and constantly behind.
That 13 hertz is the difference between a smooth operation and a robot that looks like it's always correcting itself after the fact.
And that's a great point. They even noted the smaller 2B model wasn't faster than the 3B because it needed a higher input resolution. It just shows latency isn't only about parameter count. That visual processing sequence length matters just as much.
Okay, so finally, the action expert brings it all together.
It does. Its inputs are the language goal, the current semantic context from the understanding expert, the robot's own proprioception data, and, this is the critical part, those predicted future latent tokens from the generation expert.
So the action prediction is genuinely foresight aware now. The network has literally factored in its own guess about the future before it decides what to do.
Precisely. And to predict the action, they used a flow matching objective. This is a vital detail. Standard regression really struggles in robotics because there's often more than one good way to do something, right? You get this multimodal action distribution.
Yeah, you can't just average 2 good actions and get another good action.
Exactly. Flow matching is just mathematically superior for handling that kind of ambiguity. It gives you more stable and nuanced control signals.
Okay, and how is that strict information flow from understanding to generation to action maintained inside one transformer?
They use something called a cumulative segment mask. You can think of it like an enforced set of dependencies. The mask makes sure the generation tokens can only pay attention to the understanding tokens that came before.
I see.
And then the action tokens can attend to both the understanding and the generation tokens. It's a one-way street of information. The action block gets to see the notes from the foresight block, but nobody can go back and change that initial high-level understanding.
Let's move to that second pillar of their success, the data strategy. Because for an architecture this complex, the data needs must be huge. Can you tell us more about this data pyramid they built?
The structure is really smart. At the bottom, you have the foundation layer. That's where they pre-train, mixing massive synthetic data with large-scale open-source robot data. Then at the apex, the top, you have the post-training layer, where they use a small amount of specialized real-world data for fine-tuning.
And focusing on scale for a second, What did InternData-A1 bring to the table on the synthetic side?
InternData-A1 is just vast. It's over 630,000 trajectories, something like 7,400 hours of simulation. And it's designed purely for diversity and scale, covering 4 different robot types and 70 tasks.
And it includes complex physics, right?
Yeah, stuff like manipulating deformable objects, fluids, things that are incredibly hard to capture in real-world datasets at scale.
And then Agibot World comes in to provide that real-world anchor to correct the physical fidelity.
Correct. Agibot World provided over 1 million trajectories across more than 200 tasks in 5 domains. Domestic, industrial, you name it. This is where they inject that authentic physical dynamic to ground the diversity they get from the synthetic data.
So when they mixed them, the pre-training recipe was about 533 million frames, roughly 57% synthetic and 39% real. I did notice they set the hyperparameter lambda, which balances the foresight loss against the action loss, to 0.01. That's a tiny weight on the generation side.
That's a great catch, and it's very intentional. What they're signaling is that the foresight module is primarily a guide. It's an inductive prior, not something that's meant to dominate the whole optimization process.
So the action is still king.
Action accuracy is paramount. The foresight prediction is just there to provide that future-aware context that steers the policy away from purely reactive behavior.
Foresight steers, action executes. Makes sense. One last implementation detail. This load balanced parallel training, or LPT. It sounds like an engineering fix, but why was it so crucial?
It was an absolutely critical engineering fix. When you're training on a huge distributed cluster and you're mixing data sets of wildly different sizes, like a massive synthetic one, and a slightly smaller real one naive data loading causes all sorts of instability.
What kind of instability?
Well, the workers get bogged down with I/O contention, you get out-of-memory errors, and crucially, the smallest data sets can get implicitly overweighted because they load faster. The network starts accidentally prioritizing the less diverse data.
So LBT just makes sure the resource usage is uniform and the training doesn't fail or get skewed.
Exactly. It uses size proxies and a greedy algorithm to ensure a uniform load per worker, which stabilizes the whole process and makes sure the dataset ratios you intended are actually what the model sees. It's how you scale these foundation models robustly.
Okay, let's get to the results. How did this ambitious architecture and data strategy actually perform in the real world?
They evaluated it across 3 physical robots, covering bimanual and contact-rich tasks, and the overall performance jump is really solid. The 3B model got a 75.1% average success rate in general tasks.
And that's the 14.5% absolute gain over the baselines.
It is, and what's really telling is that even their smaller 2B model at 64.7% still outperformed the larger 0 model. So it validates that the architectural efficiency isn't just about throwing more parameters at the problem.
Yeah, and the model absolutely nailed complex, fine-grained tasks. I think it got 93.3% success on Make Sandwich. That shows really robust sequence execution.
But the real fireworks, like we said at the start, were in those specialized high dynamics tasks. These are things that require instant reasoning about momentum and inertia.
Like sorting packages on a fast-moving track.
Exactly, or picking ingredients while they're in motion. The baselines, the MLLM-based models, they just couldn't handle it.
How bad was it for them?
It was terrible. Baselines like 0 were below 40% success in express sorting, and they only hit 20% success in the hardest task, which was this multi-robot in-motion ingredient picking. They're just inherently reactive, always one frame behind.
And InternVLA-A1 essentially solved this failure mode.
Completely. In express sorting, the 3B model hit 80%. In that multi-robot picking task, the most complex dynamic scenario, they achieved a remarkable 93.3%.
That's the 73.3 percentage point improvement.
That's it. And it is definitive evidence. It proves that internalizing visual foresight is the necessary component to get robotics from static reactive control to robust dynamic interaction.
Let's spend a minute on the ablation studies because they really confirmed the core design choices. First up, the importance of pre-training.
It proved to be absolutely indispensable. When they trained the 3B model from scratch, without those 700,000 pre-training steps, it resulted in a catastrophic 51.6% performance drop. Success just plummeted from 77% down to 25%.
Wow, so you just can't get to generalist capability without that massive foundational knowledge.
No chance. And then they tested the generation expert itself, the foresight module. Was it really essential across the board or just for the dynamic tasks?
And the answer was?
It was essential. Removing it caused a huge performance drop from 77% down to 57.6%. That's almost a 20% loss. And crucially, foresight was shown to be necessary in 11 out of 12 real-world tasks, not just the conveyor belt ones.
So even in seemingly static tasks, predicting the physics outcome of your action helps stabilize the policy.
It does. And finally, they validated the hybrid data approach. Did the synthetic data, InternVLA-A1, actually work as a good proxy for real-world diversity?
And it did.
It did. On its own, it performed really well, matching models trained purely on real-world data. But the mixed hybrid approach yielded the absolute best real-world results, especially in fine-grained tasks like sort parts, which saw a 20% improvement over using only real data.
It solidifies that idea. Synthetic brings the scale, real data brings the precision.
That's the formula.
So InternVLA-A1 marks a huge step forward. It successfully bridged that gap between high-level semantics and the messiness of physical dynamics.
That summarizes it perfectly. But, the authors were very transparent about the trade-offs they made, and those limitations really point to the next phase of research.
What were they?
The first is semantic. The current understanding expert, as powerful as it is, wasn't jointly trained on external VQA or visual question answering datasets.
Yes,
Which means that while it's great at interpreting instructions for the manipulation task right in front of it, its ability to handle more general semantic reasoning or really complex long horizon instructions is a bit degraded compared to a pure state-of-the-art MLLM.
It's a trade-off they made for control performance. And the second limitation goes back to that 13 hertz frequency.
Yes. That aggressive 32 by 32 to 4 by 4 latent compression in the foresight module, while totally necessary for real-time speed, does sacrifice some visual prediction fidelity. They chose action latency over perfect visual granularity.
But the spectacular gains in dynamic tasks prove that architectural choice, internalizing those causal action environment dynamics, is the right path forward for robotic robustness.
It is, and this raises a really fascinating and important question for everyone working in embodied AI. Since this architecture proved that internalizing causal dynamics is the key, what future work is needed to truly unlock robust generalist policies when these dynamics models are eventually combined with the vastly enhanced VQA capabilities needed to understand any arbitrary, complex, long-horizon human instruction? That unification, that's the ultimate final challenge.